So we already started to see last lecture that when you want a certain voltage to be the source for your circuit, you might have issues when you connect up your circuit to the source because it loads the source. And so we're going to talk about sources. I would say it causes a lot of confusion, but I don't think it needs to. So it's my own perspective. But I do think that it's not too bad once you see why this happens. So sources, also known as supplies, supply power to a circuit. There are two primary types, voltage sources and current sources. So an ideal voltage source provides exactly the voltage a user specifies, independent of the circuit to which it is connected. Okay? All it must do in order to achieve this is to supply whatever current necessary. So say you have a source that's supposed to supply 10 volts. No matter what you connect it to, it's supposed to supply 10 volts, and it's going to put out as much current as it needs to make that happen. So that's an ideal supply. There are approximations of this that are real supplies, but we'll talk more about real ones in a little bit. But we'll talk about an ideal voltage source for now. In the circuit shown, determine how much current and power the ideal voltage source, Vs, must provide in order to maintain voltage if the resistance of the resistor it's connected to is infinitely large, approaches infinity, and if R approaches 0. So what are those two things called commonly? As R approaches infinity...
Limits.
Sorry?
A limit?
Well, yeah, so that is a limit mathematically, but as R approaches infinity, physically we would say that that's like an open circuit, right? There's essentially an infinite resistance in between the two. It's like you never connected them at all. So that's an open circuit. What do you guys think about if R goes to 0?
That's a short.
That's a short circuit. It's like if you connected a wire between the two terminals. Which, it's really common to say, oh, you know, your connection's bad, it's probably a short. Well, it's probably the opposite. It's probably just disconnecting. But it's really, I don't know, we all like to say it's probably shorted out, that connector, you know, I don't know. If it's shorted, probably it would catch fire if it wouldn't just not flow power. It probably would flow a lot of power, and then your lights would dim or something. So, okay. So, let's do, you know, this is a basic circuit. We can do a little circuit analysis on this. So since, whoa, fat marker. So we have, since the voltage across the resistor is known to be Vs, so since we know that VR is equal to Vs, how do we know that? I mean, that was... Yeah, I mean, it's pretty much just pretty obvious, but technically we are using implicitly Kirchhoff's voltage law, right? That around the loop they have to add up to 0. Yeah. So, okay. VR is equal to Vs. And Ohm tells us that the voltage, or the current through the resistor is equal to the voltage across the resistor, which is Vs, divided by R. Okay? What about the power? What is the formula for the power that a resistor is dissipating at any instant in time?
Voltage times current.
Voltage times current, right? So we have IR times VR. And we have an expression for VR and IR now. So it's just Vs squared over R, right? Good. So now let's take the limits. So let's do first the open circuit. Open circuit, we've got that I'm going to just do like a sub-infinity here. So as I approaches infinity. I infinity is equal to the limit as R approaches infinity of Vs over R. Okay. What is that limit? So as R goes to infinity, the fraction goes to 0, right? Mm-hmm. 0 amps. The power, if you're flowing no current, that makes sense, right? It's disconnected. It's not going to flow any current. So the power for an infinite resistance is, how much power is going to be dissipating? It's Vs squared over R, so you could take the limit, or you could just take the product of 0 and whatever Vs is, and that's going to be 0, right? So 0 watts. So not too bad. We discovered that if you don't connect anything between two terminals, you don't dissipate power. Whew. That's good news. Otherwise, we would have a lot of trouble maintaining any energy in anything. So let's see what happens if you do the short circuit, though. Short. So what happens to the, so I'll call this I0 resistance. So it's the limit as R goes to 0, and it's on the side, of VR over R. What is that equal to? Or what does that approach? It's probably the better way to say it. Approach is infinity, right? Infinity amps. Which, I made this joke in the last class. I'm always like, I don't like repeating jokes, but I liked this one, so I'm going to repeat it anyways. Infinity amps. That would be a good band name, right? We missed out. This was a good choice. Now we're set, though. We can't go back on our word. If anybody ever starts up a band, remember what you said in this class. I wrote it down, I'm sure. Okay, so what about the power then? What happens to the power with their 0 resistance? Yeah, so the power also approaches infinity. Woo. Infinity watts, also not bad. So that's bad news, right? Because we know we can't actually do that. There's no power source that's going to give us an infinite amount of power. So we know that these idealized sources can't really be realized. So we'll look at an ideal current source first, and then we'll look at what happens when you want to make a real source. Okay? So ideal current sources provide exactly the current a user specifies, independent of the circuit to which it's connected. All it must do in order to achieve this is to supply whatever voltage is necessary to make that current flow. And we assume that an ideal one would do so. So let's do the example. It's very similar. So we can look at this circuit and say, oh, okay, once again, we can write that, Ohm's law for the resistor isn't going to surprise us because we already used it. But now instead of the voltage across the resistor being specified, it's the current, IS, that's specified by the source. So we have that from Ohm. And then power dissipated by the resistor, is going to be, well, what is, so we said it was IR VR in the last example. So our IR is, we already said, it's IS, right? And VR is ISR, so we can just square that IS and R. And you probably have seen both of these power formulas before, right? V squared over R is what we got in the last example. I squared R is what we got in this example. That's what happens when you mix VI and Ohm's law together. So, good times. Okay. So that's what we've got. Let's take our limits now. So let's do, for this time, let's do the short circuit first. So let's do the short first. So R goes to 0. So our VR is going to, as you go, take R to 0 in this expression up here, what does VR equal? 0. So 0 volts. What about if you take R to 0 in this expression? Also 0. So PR is also 0 watts. All right. So if you short out a current source, nothing flows. Okay. Or I shouldn't say nothing flows. Everything flows, but there's no voltage drop, so there's no power. But I mean, if a real wire has some resistance, so this is never really going to happen. But say you did. All right, and let's go up here to do the open circuit. Open circuit. So R goes to infinity. So say we disconnected the terminals for a current source, ideal current source. What's going to happen? You can think of this thing. I mean, current's flowing, which means that charge is like piling up at the two terminals. It's just getting crammed on more and more and more and more current. And so what's going to happen to the potential difference between those two terminals? The voltage is going to increase and increase and increase, and since it's just going to keep going, that means that our voltage is going to go to infinity, right? So our V infinity is going to go to infinity volts. And our power infinity is going to go to infinity watts. Sweet. Once again, problem. Can't do that either. Dang. But, you know, that's what you get when you have an idealized mathematical model for something. Doesn't always reflect reality, right? We can't do that, but it's still a useful model as long as we don't expect it to reflect reality in these limits. Now, modeling real sources. So no real source can produce infinite power. Some have feedback that controls the output within some finite power range. So actually, we'll talk about feedback next semester in system dynamics and controls, that class. But we don't know how to do it yet. But I'll just say it's possible to use feedback to control what a source's output is. So you can have a voltage source with a controlled output voltage that will supply more and more current to try to make its output terminals stay at a certain voltage, no matter what you connect to it. That's not what a battery does, though, and that's not what a lot of sources do. So we want to be able to model both. And also, of course, even these sources with feedback can't supply infinite power. So there's a certain point at which it can't supply that power. So you have to stay within its specs to supply the correct voltage or the correct current if it's a current source. All right, but let's say, so say if you wanted to model one of those, you would say, oh, it's ideal as long as we stay inside the operating regime. Just treat it like an ideal source. If you want to model a real source, like a battery, or like a lot of even benchtop power supplies, it depends on the power supply. you have to know what kind it is. It is either going to be one where you set a nominal voltage and then whatever you actually get, you have to measure, or it's going to be one that shows you what you're actually getting. So you got to know what you're working with. The difference between the two, you got to be careful. So, when the sources that don't have feedback in them are connected to a circuit, they're loaded. We say that they're loaded, and so they're delivering some power. They can't maintain their nominal output. So, say you had a 9-volt battery, and you put it across even like a kilo ohm resistor, or if you put it across a 100 ohm resistor for sure, you're going to be flowing quite a bit of current through that, and you're not going to maintain the nominal 9 volts of the battery. It's going to drop, right? So we model these types of sources as ideal sources in series or in parallel with a resistor, as illustrated in this figure. I don't know why the reference didn't work, but figure 1.2. So a real voltage source model is an ideal voltage source in series with a resistor, okay? And ideal current source, we do a lot more voltage sources than we do current sources, but there are current sources, so it's good to mention them. A current source, a real one, is going to be modeled as an ideal current source in parallel with a resistor. And the effect this has is that it limits the power that you can supply. So if you try to flow more and more current through this load, so say you shorted this out, for instance, that would be like the maximum amount. So if you put your load on and it was just a short, just a wire, this isn't going to supply an infinite current to that, right? It's just going to supply whatever Vs over R is current. So it limits the power output. And it's not exactly a perfect model. The power curve for a lot of real sources has like a knee in it, but this is a linear approximation for that. And since linear is a lot easier to work with, we assume that it's linear. We'll talk more next time about how to estimate what this is for a given source, so like a battery, for instance, or a benchtop supply. The term for this is the internal resistance, or sometimes the output resistance of an instrument or of a source. So it's important. It's like one of those things that I feel like just causes all kinds of headaches for people when they're first working with electronics, but it's really not that mysterious. It's just apparently so. So the confusion is just all in your head. So, all right, yeah. Any questions before I let you go? Homework questions? Friday.
So the quiz is going to be on Friday?
It'll be on Friday, yeah, by midnight. I'll probably open it around noon-ish, lunchtime. I say lunchtime because that gives me like a window.